Good morning, everybody. I feel like it's a little more light in here. But that's a little bit of improvement there. Let's get the usual things going. Where's the attendance form? Oh, where's the attendance form? There it is. There's the attendance form. Go ahead and fill that out when you have a chance. No, that's annoying. Go away. All right. That reminds me, actually. I should open that. So you guys are doing lots of things in your classes, which is really great. Of course, everyone is in very different places. So I suppose we should start. Actually, there's something else I had. Oh, I know. We'll get there in a minute. There have been some requests for some integration by parts videos, which I'm definitely happy to make. I will try and get those made this afternoon, where I can just do a bunch of different examples of integration by parts. That said, we can certainly also talk about integration by parts today. But I just want to ask you guys, is there anything specifically you would like to see today? Partial fractions, all right. Definitely look at that. Here's the attendance form again. Okay, well, I guess I'll start with some partial fractions examples. And what I would just, if you have other things you want to see, feel free to write them in the chat. I definitely know there's some different things you guys have said. Especially for those of you in FAM's class, you should speak up if there are different things you want to see. Not that you aren't, but I feel like I'm hearing more from the Mercs people, which is fine, because you guys are definitely moving faster. But if there are things that the FAM people want to see, let me know, and I will try to make it happen. So we'll do some partial fractions. So actually, yeah, okay. So I should look at one thing really quick, just to verify something. So I'm gonna look at his notes real quickly just for a second so I can see one thing. Yeah, okay. Oh, man, okay, that's. All right, he's really doing all the partial fractions. Okay. All right. Riemann Sum. Okay, methods. Yes, we can look at all those things. Okay. Sure. All right, so let's look at a couple partial fractions examples, and then we'll come back around. So what I want to say about partial fractions is really just algebra. And I think you guys aren't doing any of the ones that are really, really terrible, but we'll make sure to see. So an example of this could be something like the integral of, let's make this. So these numbers are probably going to turn out to be terrible, which is fine. Well, let's say it's something like this. X to the fourth over x minus, that's going to be terrible. I don't want to make it that terrible. Let's make it, sure. X to the fourth plus 3 over x squared times x minus 1. Yes. So looking at this integral right off the bat, I see that the degree on top is higher than the degree on the bottom, right? I have a fourth degree on top. If I multiply at the bottom, it would be a third degree polynomial. I can't use partial fractions yet, because you have to have a rational function where the degree on top is less than the degree on the bottom. So before I can use partial fractions, we have to use polynomial division. So we're going to re-express this by saying, well, the top, x to the fourth plus 0x cubed plus 0x squared plus 0x plus 3 divided by the denominator, which would multiply out to x cubed minus x squared. So if I do this division, what do I multiply by x cubed to get x to the fourth? I get x. X times x cubed is x to the fourth. X times negative x squared is minus x cubed. We subtract. X to the fourth minus x to the fourth is 0. 0x cubed minus x cubed is plus x cubed. Bring down the next term and repeat. What do you multiply by x cubed to get x cubed? 1. 1 times x cubed is x cubed. 1 times negative x squared is negative x squared. Subtract. X cubed minus x cubed is 0. 0x squared minus x squared is x squared. And now x cubed doesn't go into x squared anymore, so we're essentially done with the polynomial division process. What this means is that this fraction, x to the fourth plus 3 over x squared times x minus 1, can be rewritten as this quotient, x plus 1, plus, I bring those down, this remainder, x squared plus 3, divided by this divisor, which is x cubed minus x squared, or x squared times x minus 1. And so now that we've do fraction division, yeah, sure. I can definitely do a video of that later. Let me write that down so I don't forget to do it later. Polynomial division, sure. So yeah, I can definitely do more examples of this later. It's a pretty straightforward process once you've seen it a couple times, but it does take some practice. But the whole point of it is that we can use polynomial division to say that this polynomial is really just x plus 1 plus some leftover remainder over the original denominator. And then I can integrate this by integrating this. And this part's going to be easy. Right? The integral of x is just x squared over 2. The integral of 1 is just x. But then this part is where I'm going to have to actually use partial fractions. So this x squared plus 3 over x squared times x minus 1. Now I'm in the situation where I have a rational function I'm integrating, right? The top is a polynomial, the bottom is a polynomial, and the degree on top is 2, which is strictly less than the degree on the bottom, which is 3, right? If I multiply this out, it's x cubed minus something. So this is kind of a special case, maybe not special, but when you have something like this, if you are thinking about using partial fractions, you have to make sure that the degree on top is less than the degree on the bottom before you can do that. All right, so now we're going to look at this. And we'll come back to this side. So this is going to be equal to x squared over 2 plus x plus some integral that we will figure out how to decompose. So I'm going to rewrite this fraction, x squared plus 3 over x squared times x minus 1, as a partial fraction decomposition.
James, could you please back over for a second?
Sorry, let me turn my volume here. I didn't quite hear you. Say that again?
Could you flip over for a second?
Sure, let me just finish erasing this.
Thank you.
Was there a question or just something you didn't quite get yet?
I just wanted to take a picture of it.
Oh, sure, of course. Also, I'll mention just in general, I do post the videos later, so if there's something you missed, you can always go back and look, but no problem waiting, that's all. The board is starting to feel like it's a little bit like wants to fall over. Not really, but like it feels not super stable. So we're taking this fraction, x squared plus 3 over x squared times is x plus 1, x minus 1. And we're going to write this as a partial fraction decomposition. So when I look at this, first of all, the denominator needs to be factored. It is, it's completely factored. So I look at each factor, and I see that I have x to a higher power. So when I have x to a higher power, or anything to a higher power, I need all of the lower powers as well. So I don't just need something over x squared, I need something over x and something over x squared. Right? You need that power of x and every lower power. So just as another example, if you were doing something like, I don't know, 3x plus 5 over x cubed times x minus 1 to the fourth, this would be terrible. But the way you would write the decomposition would be, it would have 7 pieces. You would need to write it as a over x plus b over x squared plus c over x cubed plus d over x minus 1 plus e over x minus 1 squared plus f over x minus 1 cubed plus g over x minus 1 to the fourth. I'm just pointing that out to really emphasize that if you have something to a power other than 1, you need every lower power as well. So I need both these powers of x. I leave myself enough room. Sorry, I'm going to erase this x. It's not really that important. And I also have x minus 1 to the first, so I need a c over x minus 1. Okay, we're just doing algebra. We're just going to multiply both sides of this expression by this common denominator. So we're going to multiply everything by x squared times x minus 1. And the whole point of this is that it's going to get rid of all of our denominators, right? When I distribute this over here, this times this just cancels the denominator. So I get x squared. Ooh, excuse me, I get x squared plus 3. And when I distribute to each of these 3 terms here, the stuff in the bottom is going to cancel out. So when I multiply here, one of the x's cancel. So I get just x to the first times x minus 1. When I multiply here, the x squareds cancel. So I just get b times x minus 1. And when you multiply here, the x minus 1's cancel, and you get c times x squared. So that's always going to happen when you're doing partial fractions. All the denominators are going to cancel out. And then our job is to solve for a, b, and c. These things have to equal each other no matter what x is equal to. That means we can pick any value of x we want. Specifically, we can pick some nice convenient values of x. So there's the attendance form again. Make sure everybody go fill it out. Please, you guys have been doing a good job filling it out. It makes my job way easier when you do it, so thank you. So we're going to pick convenient values of x. Specifically, really the values of x we pick are the values that make these denominators undefined. So I'm going to pick x equals 0, I'm going to pick x equals 1. Because those values are going to make lots of these terms go away and make it easy to solve for the other ones. So I pick x equal to 0. On the left, I get x squared plus 3, so 0 squared plus 3. On the right, I get a times 0 plus b times negative 1 plus c times 0. So negative b equals 3.
Oh.
Go ahead. Sorry, it sounds like someone might have had a question. All right, well, if you have your question, don't hesitate to speak up. In the same sort of way I picked x equal to 0, I'm also going to pick x equal to 1, because x equal to 1 is going to make this term 0 and this term 0. So I pick x equal to 1, I get 1 plus 3 on the left, so I get 4, equal to a times 1 times 0, so I'm not going to write that down because it's 0, b times 0, also 0, and c times 1. So I get c equal to 4. All right. So here's the thing, and this is always true if you have factors that are repeated, meaning if you have x to a higher power than 1, or something like x minus 1 to the third, if you have a power where you're repeating that factor and having all the lower powers of it, you're always going to run out of convenient values of x to pick before you actually find all of a, b, c, d, whatever. So after you found all the easy ones, then you have to do something else. My personal preference, and I think it's not just because it's what I like, because I think it's the easiest, is what's called equating coefficients. So usually I wouldn't do all the work I'm about to do, but I'm going to do it here. I'm going to multiply the right-hand side to kind of see what each power of x's coefficient is. So on the left, I have x squared plus 3. On the right, if I multiply this out, I have ax times x, which is ax squared, and ax times negative 1, which is minus ax. Here I have b times x minus b, and I have c times x squared. And then if I wanted to, I could group the powers of x together. So I have an ax squared and a cx squared. So I have a plus c times x squared. I have a negative ax and a positive bx. So I have a negative a plus b times x. And I have a negative b. And I can use that to figure out whatever I need to still solve for, which I guess is a, right? So here's the thing. And this is always true for polynomials. If two polynomials are equal, the coefficients of each power of x have to be equal to each other. That's why it's called equating coefficients. If I have 1x squared on the left, I have to have 1x squared on the right, meaning a plus c has to equal the coefficient of x on the left, which is 1. So equating coefficients tells me a plus c has to equal 1. But since I know that c is equal to 4, I can use that to solve for a. So a is equal to 1 minus c, which is 1 minus 4, which is negative 3. So typically, that's how you find the leftover ones, by equating the coefficient and saying, oh, this coefficient has to equal that coefficient. And here, if you had more work to do, you could say, oh, negative a plus b has to equal 0 because there's 0x on the left and there's negative a plus bx on the right. That would mean a has to equal b, which is what we're getting, right? A is negative 3 and b is also negative 3. Okay, and we finished the partial fraction decomposition. We got a and b both equal to negative 3 and c equal to 4. But then we're not done. So then we go back to our integral and we say, oh yeah, this fraction we can now write as negative 3 over x plus negative 3 over x squared plus 4 over x minus 1. We're just plugging in the values for a, b, and c. Instead of writing plus negative 3 over x squared, I'm going to write minus 3 over x squared and 4 over x minus 1. And each of these things are supposed to be relatively not terrible to integrate. So I'm kind of out of moving. So let me erase this. Knocking things over. So we're going to go up here and say this is equal to, I still have this part here, x squared over 2 plus x. Ignoring the negative 3, right? So when I see negative 3 over x, I'm really thinking of this as negative 3 times 1 over x. And instead of negative 3 over x squared, I'm really thinking of this as minus 3 times 1 over x squared, or x to the negative second. And instead of 4 over x minus 1, I'm thinking of it as 4 times 1 over x minus 1. And I know the integral of 1 over x is the natural log of the absolute value of x. I know the integral of x to the negative second is x to the negative first over negative 1. Like minus 3 times x to the negative first over negative 1. And the integral of 1 over x minus 1 is the natural log of the absolute value of x minus 1. So I get 4 times the natural log of the absolute value of x minus 1 plus c. The only simplification I would do here is I might rewrite this as positive 3 over x. So my final answer would be x squared over 2 plus x minus 3 natural log of the absolute value of x plus 3 over x plus 4 natural log of x minus 1 plus c. Are there questions about this example?
I had a question.
Sure.
When you're going back and finding the partial fraction, does it matter which, I guess, term you're putting under the a and the b and the d? Okay.
The only reason it matters ever is if you're comparing your answer with someone else, they might have different letters corresponding to different things, so it might not look exactly the same. But eventually the answer will always turn out the same. Doesn't matter which way you write it.
Okay, thank you.
And some people have different conventions. My convention typically is, if I've written it factored this way, I'm going to write the x thing first, and I'm going to write the lower powers of x first. But look, so if I've written this as x minus 1 times x squared, I probably would have written it as a over x minus 1, and then b over x and c over x squared. But no, it doesn't matter anymore.
Okay, thank you.
Okay, I have a question for you guys. So, how do I phrase this the right way? I don't think Merckx did any examples like this, but I just want to make sure. So, did he do an example where you were integrating something like x plus 2 over x minus 1 times x squared plus 1? And before you say yes or no, let me show you how the partial fraction decomposition works. This works by writing x plus 2 over x minus 1 times x squared plus 1. Now, x squared plus 1 can't be factored, so it's called an irreducible quadratic factor. And the way you would do the partial fraction decomposition would be to do a over x minus 1. And instead of, so the thing is, since this can't be factored and it's a second degree polynomial, there's this special thing you have to do where you say, oh, for this piece, instead of just saying it's b over x squared plus 1, you actually have to say it's bx plus c over x squared plus 1. So let me ask you guys, does this look familiar at all? Has he talked about this? My expectation is no, but I want to make sure. Yeah, okay, good. That's what I thought, but I just want to make sure. Okay, so we won't talk about this unless you have to. I know he did allude to something else about integrating 1 over x squared plus 1. We will cross that bridge when we get there. So let's do one more partial fraction example, and then we will move on. And let me actually give you just 1 second to make up something that's a little more interesting, but it takes a minute to make sure the math comes out right. So let me just, now's a good time to grab your water if you need a minute. I'm going to just think of something real quick here. Let's make it not too awful. Sure, let's do that. Sorry, it's hard to make this come out exactly nice every time. So, sure. Yeah, that'll be fun. Okay. Sorry, fun being, you know, code for awful. So I need to multiply this by. All right, 1 second, almost there. That. All right, got it. So I want to find the interval. This is good. So here is a good word of advice. If a thing that looks like it's going to be a partial fraction looks awful, it's usually because it means that someone has done the job of actually making the numbers come out nice. So you should actually kind of be happy if a partial fraction looks terrible, because it usually means the numbers are actually going to be not too terrible to find. So here's what I've got. I've got the integral of, it's kind of big, 3x to the 4th minus 3x cubed plus x squared minus 2x plus 1. This might turn out awful because I might have made a small mistake. I don't think I did, but you never know. And the denominator is going to be x to the 5th minus 2x to the 4th plus x cubed. Which looks pretty gnarly. So definitely, I think I can use partial fractions, and I think I can because, well, one, the degree on top is definitely less than the degree on the bottom, And 2, it looks like the denominator factors. It definitely factors. So this factors as, in fact, let's just write out, so I'm going to write 3x to the 4th minus 3x cubed plus x squared minus 2x plus 1 divided by, I'm going to factor out x cubed. If I factor out x cubed, I'm left with x squared minus 2x plus 1, but that factors as x minus 1 squared. So there is my denominator factored, right? This is x cubed times x squared minus 2x plus 1, right? Yeah, and then that other piece factors a little more. And so there's going to be 5 pieces in my partial fraction decomposition. A over x, b over x squared, c over x cubed, d over x minus 1, e over x minus 1 squared. Okay, and now we do the thing where we multiply both sides by the common denominator. So I'm multiplying everything by this. So here's what we end up with. So the left-hand side, you always just get the numerator. So you get 3x to the 4th minus 3x cubed plus x squared minus 2x plus 1. On the right-hand side, you get all the pieces without the denominators, and you're always going to be canceling. So like for a over x, I'm going to cancel out one of the x's and get a times x squared times x minus 1 squared. For b over x squared, I'm canceling out the x squared, meaning b times x times x minus 1 squared. For c over x cubed, I'm canceling out exactly the x cubed, meaning c times x minus 1 squared. For d over x minus 1, I'm canceling out one of the x minus 1s, meaning d times x cubed times x minus 1. And finally, for e over x minus 1 squared, in fact, I'm canceling out both the x minus 1 squareds, meaning e times x cubed. Barely fits. Which looks really, really terrible. It's not as bad as it looks. So again, we're going to pick the convenient values of x, which does d have x cubed? It does. It's d times x cubed times x minus 1. Because again, I'm going to multiply this by this. The x minus 1 cancels out one of those x minus 1s, but we're still left with an x cubed times x minus 1. Definitely. So on the left-hand side, we have 3x to the 4th minus 3x cubed plus x squared minus 2x plus 1 equal to a times x squared times x minus 1 squared plus b times x to the 1st times x minus 1 squared plus c times x minus 1 squared plus d times x cubed times x minus 1 to the 1st plus e times x cubed. And then we're going to pick the convenient values of x. There's only 2 convenient values of x. It's just the things that make the denominator 0. So x equals 0 and x equals 1. For x equals 0, I get 0 minus 0 plus 0 minus 0 plus 1 equal to 0 plus 0 plus not 0, right? 0 minus 1 squared is 1, so I get c times 1 plus 0 plus 0. So here I get c equals 1. Plugging in 1 for x, I get on the left 3 minus 3 plus 1 minus 2 plus 1. I'm just plugging in 1 for x, just gives you the coefficients. And then I think that's going to be 0 on the left. That's a coincidence. On the right, I get a 0 here, a 0 here, a 0 here, a 0 here, and a 1 there. So 3 minus 3 is 0, and 1 plus 1 minus 2 is 0. So e equals 0. And now we need to equate coefficients. So I probably need to write this on the other side. Which is going to be kind of a pain. Oh well. Okay, so here's what we have. We have 3x to the 4th minus 3x cubed plus x squared minus 2x plus 1 equal to, sure, a times x squared times x minus 1 squared plus b times x minus 1 squared c times x minus 1 squared plus d times x cubed times x minus 1 plus e times x cubed. And so now, oh, we also, sorry, we found that c is equal to 1, e is equal to 0. But we've run out of convenient values of x. Wait, isn't it minus x squared? I have a plus x squared.
I think I wrote it down wrong.
Okay. So now we're going to equate coefficients. And so I always start with the highest power I have in either side, meaning I'm going to look at the coefficient of x to the fourth. The left-hand side is usually pretty easy. On the left-hand side, I have a 3x to the fourth. On the right-hand side, it's less easy. I don't really want to multiply all x. It's kind of a giant king. So I have to be kind of careful and say, okay, if I look at this term, if I multiply it out, would I get an x to the fourth? And the answer is yes. This would be a times x squared minus 2x plus 1, which would give me an a times x to the fourth. If I multiply out this term, would I get an x to the fourth? And the answer is no. I'd have x times x squared giving me the highest power of x cubed. Same thing true as here. I don't get an x to the fourth. I do get an x to the fourth there, right? I get d times x to the fourth minus d times x cubed if I distributed that. So I do get a d times x to the fourth. I'm only interested in the x to the fourth terms. So here, I get 3 equal to a plus d, which doesn't help me yet because I don't know what either a or d are. So I move to the next coefficient. I move to x cubed. On the left-hand side, I have a negative 3x cubed. On the right-hand side, it's going to be a little bit trickier, to be honest. So I'm going to multiply this one out just so you guys can see it a little bit. This term right here is a times x squared minus 2x plus 1. And if I distribute the x squared, I get a times x to the fourth minus 2x cubed plus x squared. So I do have an x cubed term, and the coefficient of that x cubed term would be a times negative 2. So I'd have a negative 2a x cubed. My a looks like trash. And then looking at this term, I would also get an x cubed, because this is b times x squared minus 2x plus 1. And bx times x squared is an x cubed term. So I have a b times x cubed. I don't get an x cubed term here, because I just have x squared. Here I do get an x cubed term. Right, this is going to be dx to the fourth minus dx cubed. So I have a minus dx cubed. And I also have an ex cubed. A 3. I know things are looking bad, but really it's going to get better. So here's what I've got. I've got negative 3 equals negative 2a plus b minus d plus e. But e is 0. Right, we already found e is equal to 0. So looking better. Not quite there, but we're almost there. Let's look at x squared. It's the same kind of deal. For x squared, I'm going to have an a times x squared. Oh, sorry, on the left-hand side, I have a positive 1x squared. On the right-hand side, I have a times 1x squared, so I have 1a. I have a bx times a negative 2x, that's going to give me a negative 2bx squared. Notice I've stopped writing the x squared and I'm just writing the coefficients because I really just need the coefficients. For c, I do have a c times x squared. For d, I don't have a d times x squared because each of these are higher than x squared, and the same thing for e. So I just have this. I know that c is equal to 1. Yeah, let's go and look at x as well. So looking at x, I don't have an a times x because the lowest power of the a thing is x squared. I do have a b times x, or bx times 1. Oh, sorry, I should start with the left-hand side. On the left-hand side, I have a negative 2. On the right hand side, I have a d times x. And let's see, I have a c times x because this is x squared minus 2x plus 1. So I have c times negative 2x. I have a minus 2c. And I don't have a d or an e times x. So now we're looking good, right? Because look, I know that c is equal to 1. So negative 2 equals b minus 2. Adding 2 to both sides, 0 equals b. And then if 0 equals b, I can solve for a. So this means 1 equals a plus 1. So a is also equal to 0. And then I can use that to figure out what d is, right? If a equals 0, then d has to equal 3. And I've got everything. So once you get to 1, everything else kind of just falls into place. So whoops, I'm going to fall on my chair. So I've got all of my a, b, c, d, and e. So now I can go back to what I was trying to integrate. Like, okay, a, b, and e all equal 0. C is 1 and d is 3. So c is 1. I feel like when I started this problem, I was supposed to get e equal to 3. Oh well, that's life. We'll pretend like we did it right. Yeah, that feels really. Oh no, I know I did something silly. Okay, yeah, that's right. So right, it seems like kind of a lot of work for what we ended up with, but that means we can easily integrate this as the integral of d was 3, not 1, right? Let's double check. Yeah. So hopefully you guys are seeing that most of this is just garbage algebra, right? Like it's a lot of terrible algebra. The actual integration piece is usually not too terrible. This is going to be the integral of 1 over x cubed, which I would prefer to write as x to the negative third. Right? If my power in the denominator is not a first power of x, I usually write it like that. But for 1 over x minus 1, I do like to write it as 1 over x minus 1 because it makes it clearer to me that it's going to be a natural one if it's 1 over x to the first. It's 1 over x to some other power, not a natural log. It's 1 over x to the first power plus or minus some other stuff. It is a natural log. Okay. I'm going to erase this so that I can write my answer. But really, we've done the hard work. The rest of it's just like, oh yeah, integral of this is x to the minus 2 over minus 2 plus the natural log of the absolute value of x minus 1. And I would probably write this as minus 1 over 2x squared. Right? Bring that down to the denominator. So that's how I would do that problem. It's kind of gross, I know, but it turns out not to be so bad. Okay, are there any other partial fractions questions before we move on to other things? Not that I can't do other examples or videos later, if there's specific things you guys want to see, but I think we've covered most of the partial fraction stuff you guys will probably see. Okay. All right, let me look at Riemann sums. Okay, let's see. Yeah, let's go to Riemann sums. This is fun is that. So I might need a little more context for the Riemann sums. So I'm guessing what you guys are doing, because I didn't see all of it, is that you're being asked to maybe estimate the area under a curve using a Riemann sum. Is that right? Or are you doing something different? Okay. So let me just throw out an example and see if this sounds about right. Use a, so I'm going to write it this way. Yeah, let's do it this way. Estimate the area under, what's a good example? Yeah, sure. f of x equal to 4 over x on the interval from 1 to 5 using, I don't want to make it too terrible. Let's say n equals 8 rectangles with left endpoints. Does that sound about right, or should I be modifying this in some way?
I think that looks good. We like all the examples we did in class, like he had already like graphed it out basically, and stuff. Yeah.
So is he using? Are you guys using left or right or midpoints, or are you kind of switching it up?
We used left and right.
Okay, but not midpoints yet.
It's
fine. It's not. Just one part. So we'll do this one using all three, just to kind of see the examples, unless the example ends up being terrible. I feel like n equals 8 is going to be awful. Let me not do n equals 8. Let's do n equals 4. So I will say, for this kind of question, it's nice to have a picture. You don't have to have a picture. I mean, this probably is more what Pham is doing right now. I definitely saw some pictures of rectangles from his most recent lecture, but I feel like Merck's also talked about, I don't know, Merck's notes are hard to read. I think he talked about midpoints, but I'm not positive. So, I mean, this is something that both classes should cover, but if this isn't in Merck's class, don't sweat it too much. If you're in Merck's class. So here's the idea. I'm going to estimate the area under the curve. Now here's the thing. We already know how to find the area under this curve, right? If I actually want to find the area, I would do the integral from 1 to 5 with 4 over x dx. I would get 4 natural log of the opposite value of x from 1 to 5. I would get 4 natural log of 5 minus 4 natural log of 1. I drop the opposite values because these numbers are already positive, so I don't need them. And the natural log of 1 is 0. So the area under the curve is actually 4 times natural log of 5. We're going to estimate it. And the reason you might actually do this, aside from understanding how the fundamental theorem of calculus works, is that there are some functions we actually can't antidifferentiate, and so we can't use the evaluation there. We'll actually have to use rectangles or trapezoids or some other method to estimate the area under the curve. This one we don't, but it's nice to know that we could. So here's my function, or here's my xy plane. And 4 over x looks something like, let's see, 4 over 1 is 4. 4 over 4 is 1. Looks something like this. And we're trying to find the area under this curve. So what we're going to do is we're going to draw rectangles. And so I made the interval nice. And we're exactly going to use 4 rectangles. So we're going to use each rectangle. So the length of each rectangle, I should say the width. So the width of each rectangle, which we often call delta x, is the total length divided by the number of rectangles, which in this case is just 1. More generally, it's b minus a over n. So I'm trying to estimate the area in each of these regions. And since I'm using rectangles with left endpoints, here's the thing. For each of these regions, I'm going to use a rectangle. But the rectangle area is going to depend on if I use left endpoints or right endpoints, midpoints, or some other point in between the two endpoints. So for this first rectangle, I'm using the left endpoint, meaning I'm going to use the height of the function at that endpoint to give me a rectangle. Clearly an overestimate in this particular example. Same deal here. For this second region, I'm going to use the left endpoint to find the height of my rectangle. This third region, I'm using the left endpoint. This fourth region, I'm using the left endpoint. So here's how I could write the estimate of the area. So just the areas of these rectangles out of the area. So my area here is approximately base times height plus base times height plus base times height plus base times height. Each of the bases is 1. The height here is the function evaluated at 1. Area of this rectangle has a base of 1. The height of this rectangle is f of 2. Same thing here, base is 1, height is f of 3. Here the base is 1, the height is f of 4. So our estimate's going to be an overestimate, but we're going to get, let's see, f of 1 is, well, my function is 4 over x, so it's going to be 4 over 1. F of 2 is 4 over 2. F of 3 is 4 over 3. F of 4 is 4 over 4. And that's going to be, let's see, 1 plus 4 is 5. So this is 1, this is 2, this is 4. 1 plus 2 plus 4 is 7. 7 plus 4 thirds. 7 is 21 thirds. Plus 4 thirds is 25 thirds. So there is our overestimate of this. And just for comparison's sake, 4 times natural log of 5, which is the actual area, is 6.43. 25 thirds is certainly an overestimate. It's 8.33. So a big difference there. We could also have used right-hand endpoints. So if I use right-hand endpoints instead, then for this first rectangle, I'm using 2 to find the function height. So I'm doing this rectangle here, which is actually the same as this one, but that's pretty typical. And for the second rectangle, I'm using the right-hand endpoint 3 to find the height of the rectangle. For the third region, I'm using the right-hand endpoint, which is 4, to find the height of that rectangle. And for this last one, I'm using 5 to find the height of that rectangle. So using right-hand endpoint, and so sorry, just a notation thing. People often call this first thing we found, they call this capital L sub 4 for the area using rectangles with left-hand endpoints and 4 rectangles. For this one in red, I would call that R sub 4 because I'm finding the area using 4 rectangles with right-hand endpoints. So R sub 4 would give you 1 times f of 2 plus 1 times f of 3 plus 1 times f of 4 plus 1 times f of 5, which would end up being, let's see, well, we already know f of 2 is 4 over 2. F of 3 is 4 over 3, right? It's just 4 over whatever. F of 4 is 4 over 4, which is 1. F of 5 is 4 over 5. So this gives us what? 3 plus 4 thirds times 5 over 5 is 20 fifteenths. And 4 fifths times 3 over 3 is 12 fifteenths. So I end up with 32 fifteenths, and 3 is 45 fifteenths. 45 plus 32, which is 77 fifteenths. So obviously from the picture, this should be an underestimate, right? The area in red is certainly less than the area under the curve. If we calculate 77 fifteenths, it's 5.13 about, which is definitely less than the 6.43 that is actually the area. So that's at least the very beginning of what's going on with using rectangles to find the area under the curve. What else to say about this? So let me ask, what questions do you have about this? I can definitely make a video on this as well. If you want to send me a more specific question, that'll certainly help because there's kind of a lot of different directions I can go with this, but I can definitely be general if you guys don't have more specific suggestions. So, so I'll make a video on Riemann sums, rectangles, etc. This black dust. let me do actually. Yeah. So exactly. With the left-hand sum, you ignore with the left-hand ones. You ignore that value there because again, for this interval, you're using the left-hand value, and for right-hand things, you ignore the leftmost one. Again, for this first one, you're using the right-hand endpoint. What does it mean to overestimate? It just means so. So if I look at this using so in this particular example, so it's just a decreasing function, the right-hand endpoints are going to be an underestimate because the area in red is less than the area that's actually under the curve in green. Using left-hand endpoints here, it gives me an overestimate because the area encompassed by this rectangle, or all these big rectangles, is more than the area under the curve. So that's an excellent question, Sophia. What is the point if we just integrate? Well, we can't always just integrate. That's the problem. So there are some functions that are not anti-differentiable. Not just that we don't know them, but they literally cannot be anti-differentiated. And a very kind of typical example, especially if you're ever going to take stats, is the function e to the negative x squared, because it comes up when you're talking about the normal distribution or the bell-shaped curve. So if I wanted to find, say, the area under the curve from 0 to 1 of e to the negative x squared dx. So the problem with this is I don't know how, not just I don't know, we cannot anti-differentiate e to the negative x squared. So I'm going to estimate this using, let's get an interval from 0 to, I don't want to make, it's just the numbers get gross. Let's go 0 to 3, which is going to be not too terrible, using n equals 6 rectangles. And while we certainly can draw a picture, we don't really need to. That's good. So I'm going to draw my picture. I'm not going to draw, I'm going to pretend like my curve looks like that, right? And I'm going to 6, from 0 to 6. And so if I'm, sorry, from 0 to 3. So I'm going from 0 to 3, and I have 6 total rectangles. Then the width of each rectangle, or the delta x, is b minus a over n, which is 3 minus 0 over 6, which is 1/2. So each rectangle is going to have a base of 1/2, and then each rectangle is going to have a height that depends on what kinds of rectangles we're using. Are we using right endpoints, left endpoints, or midpoints, or something else? And so let's do both right endpoints and midpoints. Yeah. So first of all, I need to break this up into 6 things. So if I know the width is 1/2, I know from 0 to 1/2, and then from 1/2 to the next one is 1, from 1 to the next one is 1.5, and then 2, and then 2.5. But you can just take the width of each rectangle and add it to the beginning space to get all the values. And then I want to estimate each of these areas. So using right endpoints, so R6 would be, so each of these rectangles has the same base. So I'm going to factor that in. There's my base of 1/2. And then I'm just going to do, I'm using right endpoints. So I'm starting at 1/2. It's going to be f of 1/2 plus f of 1 plus f of 1.5, or 3/2, I like 3/2 better. Plus f of 2 plus f of 5/2 plus f of 3. And that's how you would at least start to express the estimate using right endpoints in this curve. Now, this is kind of still gross because f of 1/2 is not something easy. So I should say, right, our function, our f of x, is the e to the negative x squared. So calculating this is not particularly fun. Right? It's 1/2 times, right, e to the negative 1/2 squared is e to the negative 1/4. And this is e to the negative 1. And this is e to the, let's see, 3/2 squared is 9/4, so negative 9/4, negative 4, negative 25/4, and negative 9. The dumb thing about this is that you still have to use a calculator. 1 second. You still have to use a calculator to find all these things. This says f of 3. I know my writing is not excellent here. Right, all of the right-hand endpoints. 1/2, 1, 3/2, 2, 5/2, 3. So yeah, I mean, we could get out of calculator and do this. I don't really think we need to, right? But we would get something. Left-hand endpoints would be virtually the same, except it would be 1/2 times. We would start here at 0, so it would be e to the 0, which is just 1, and then you'd have all of these terms, just not the last one. So e to the -1/4, e to the -1, e to the -9/4, e to the -4, e to the -25/4. If there are 6 rectangles, there should be 1, 2, 3, 4, 5, 6 things added together, representing the area of each of the rectangles. What else did I want to say here? Yeah, there's some notation you might want to be aware of. So one way you could write this, which is kind of, I don't really want to do that. The other thing I want to mention here is that there is also a way to do this using midpoints, which is a little bit messier. So if I'm going to use the midpoints, and this is where I really do like to have drawn the picture because it just makes it easier for me to see. So the midpoints, right, I'm actually going up here and using the middle value to find the height of the rectangle. And I'm using the middle value. Usually the midpoint method is a better estimate than either the left or the right hand endpoints because it kind of balances out some of the over and underness. So I was going to use those 6 rectangles. I now can't use these endpoints, right? They aren't the points that are giving me the heights. So for midpoints, for M6, the base is still the same, right? Each of these rectangles still has a base of 1/2. And now my midpoints are, well, halfway between 0 and 1/2 is 1/4. And you can either keep doing that and say halfway between 1/2 and 1 is 3/4. Or you can just say, well, all the midpoints are still a delta x away from each other, right? This length is still 1/2, this is 1/2, this is 1/2. So you can say, oh, 1/4 plus 1/2 is 3/4. And 3/4 plus 1/2 is 5/4. And 5/4 plus 1/2, which is 2/4, is 7/4. And we need 2 more because I only have 4. And an f of 9/4 and an f of 11/4. So that's how you would express that. And then you would literally just plug it in and I'm going to erase this. Our M6 will look like 1/2 times. So f of 1/4 is e to the -1/4 squared. So e to the -1/16. This is going to be e to the -9/16, and e to the -25/16, and e to the -49/16, and e to the -81/16, and e to the -11 squared, so 121/16. So this is actually why you would do something like this, because we want to know the area under this curve, but we actually can't use the fundamental theorem of calculus to find it. We only have estimation available to us. Now, my kind of gripe about this is that if you're doing all this work to estimate it, which is definitely going to require a calculator, why not just use a calculator to estimate the area in a nicer way, right? Calculators are powerful, wonderful tools. They do great things. So I think if you're doing all this, it kind of makes sense just to use it to its fullest capability. All right, what else should we say about Riemann sums? Or what other questions do you guys have?
Is the midpoint one the most accurate? Like if, or whenever you're doing it, would they just specify like do it from the left, do it from the right?
They would usually specify. They won't say like pick your favorite or pick the one you think is most accurate. they will usually say do left or right or midpoint. Typically the midpoint is the most accurate. There are times where it might not be, but they're hard for me to think of if they even are. Yeah, the midpoint is usually the most accurate. You can also take the average of the left and the rights, which is, I think, the same as the trapezoid method, which I don't think we've talked about yet. So there are other methods of estimation. And the thing about this is, you can talk about this in the context of using it to estimate, like we kind of are here, but it also shows up in the context of using these rectangles to define how the integral works. And while that's something that's kind of important, I mean, it's really important. And I know it's not beyond the scope of this class, I just don't know if it's really worth your time to go there. So if you want to talk more about kind of writing the integral as the limit of some sum of areas, we certainly can, but I think our time might be better spent elsewise. Let's see here. Let me throw up the, let me not throw up, let me put up the attendance form. All those those are all over 16 because, right, again, I'm plugging in 1/4, and 1/4 squared is 1/16, and 3/4 squared is 9/16, and 5/4 squared is 25/16, and so on. And then they all have a negative in front of them because the negative is coming after we do the squaring. Yeah, I know I'm writing something kind of small here. Let's see, I know someone else had something else. Let me go back a little bit. Oh, disk and washer. Yeah, let's talk about disk and washer. In fact, so I have something cool that a friend of mine, Sarah, found that I wanted to share with you guys. Let me find it here. So let me share my screen first. So where'd you go? Try 1 second. That's interesting. Well, I was going to share something with you guys. I think it might not be there. Apparently lots of people's internet is down. Also, my wife, she's on, so she works from home and has for a while, and she has a different internet provider than I do, and her internet provider is down, which is Wave. So hopefully that is not affecting everybody too terribly. Oh, good, there we go. So let me share my screen with you guys. Maybe, yeah, fine, okay. Yeah, I know how to do this, okay, great. So this is, hopefully this one will come up. Let's look at this one. You hate when you want to like move your thing around. Yeah, there we go. So I thought this was kind of a useful tool for visuals. Oh, geez, yeah. I'll send the link to this in just a second. Let me actually, somehow I'm drawing points that I don't need to be drawing. It's holy crap. Okay. So you can move this around. So here's what they've got here. They have got the function f of x equal to x squared over 4, which, so this one, it's kind of hard to always grab it the right way. So here we have, right, the x-axis here, the y-axis here. You've got the function f of x equal to x squared over 4. And then what they're doing, what this red part is, which will kind of move things around, is they're rotating from x equals 1 to x equals 2. They're rotating this curve around the x-axis. So let me grab this and kind of try and show you guys. And you can kind of see it there, I think. And you can change the angle as well. So you can say like, so as you start to rotate this thing around, it's going to do all of that. And it's going to make this cool kind of shape. Now it kind of shows it more as the solid, or the surface boundary of the solid shape, right? It kind of shows it more like being like kind of an empty cone. But I do think it's kind of a helpful tool for visualizing what is going on. And the other cool thing about this is it, actually no, that's not, sorry, that's for another class. You can also, so you can take the same function. And so I guess what I should say is it shows you what the integral will be, right? So the integral that we want is the integral from 1 to 2 of pi times your radius squared. And here the radius is just the function, right? It's the distance from your function to the x-axis. Ooh, that's quite unique. Play around with that. This is still a fairly new thing I'm using, so I don't exactly know all the way it works. And then if you need to, you can also talk about rotating around the y-axis, which I don't know if you guys are actually doing, but it's also worthwhile. Notice that when I rotate around the y-axis, it's still the same sort of formula, right? It's still the pi times the integral of your function squared or your radius squared, but the function has changed. Instead of being y equals x squared over 4, we have to solve for x in terms of y, and you get x equal to 2 root y, right? So if you solve y equals x squared over 4, sorry, I hope that you guys can kind of see what I'm writing here. If you solve y equals, that's terrible. If you do y equals x squared over 4 and you solve for x, you get 4y equal to x squared. And then taking the square root, you get x equal to square root of 4 is 2, square root of y is y. It would be plus or minus, but we really want it to be plus because we're where y is positive, or sorry, where x is positive. So that kind of shows you that if you're going around the y-axis. I don't know if you guys are doing a lot of that, but you might do some of it. And then you can slide this doohickey here and you can see, oh yeah, look, you get that kind of shape and you can move it all around. It's kind of cool. That's kind of neat. There's also this other thing. Yeah, okay, good, fine. So I kind of like this one because it kind of shows you, it actually shows you some of the left-right stuff we were just talking about. So if you want to say, find the volume of this function 2 square roots of x from a equals 1 to a equals 9. What's this do? Oh, that kind of changes. Sorry, a equals 1 to b equals 9. You can kind of see what that looks like. So, right, the idea is we're slicing it up into rectangles, and then we're rotating those rectangles around to get, oh, that's cool. Right, you're sliding those rectangles around to get the disk volumes. And the radius is just the height of the function. So you might use these tools. I think they're kind of neat, at least to help see what's happening. This one doesn't do the thing where it shows you what the integral would be, whereas the other one does. So that's kind of nice. But let me exit here and put those both in the chat, just so you have access to them if you want to use them. I think they're useful. So there's one of them. And there's the other one. So that said, let's go ahead and do a couple examples. Again, a couple things just before I forget. Sorry, where'd you go? There's the attendance form again, and do go ahead and email me if you guys want me to make videos of things. I've already tried to write down all the things you guys have asked about, but it's easy for me to miss things, so go ahead and I'll try and do that this afternoon. Yeah. And I'm already planning on doing some iteration by parts videos, both using tabular method and not using tabular method. Tabular is great when you can use it, but you can only use it in 3 different types of examples. So, all right, so let's say we want to find the volume of the solid, and let's do 1 disk and 1 washer. And I'm assuming you guys are mostly going around the x-axis. Is that correct? Or are you doing any around the y-axis? Both, okay. That's unfortunate, but not surprising. So let's look at, okay. The volume of the solid obtained by revolving the region. Ooh, yeah, this is a good one. Bounded by y equal to natural log of x, y equal to e, and x equal to 0 around the y-axis. most of the time, I would say you should draw a picture for these. It's just going to make your life easier. If you aren't good at drawing the pictures, use Desmos, right? So we can pull up Desmos just to remind everybody about it. Let me show you again. Let me Desmos. So sorry, let me share my screen here. 1 sec. Great, yeah, do it. Desmos. So right, we could definitely graph all these pretty easy. So y equals natural log of x, y equals e, which should just be a horizontal line, and x equals 0, which is just the y-axis. And there's probably some cool way of like getting the area between them to show up nicely. Oh, I was stupid. I wasn't stupid, but I forgot. So here's the thing. The way I've written this, I've actually kind of defined an infinite area because the natural log of x and x equals 0 don't ever actually touch. So I should throw in one more boundary, which is y equals 0. So then I'm just dealing with zoom out, I'm just dealing with the region between these 4 graphs here. And I wish I was better at using Desmos to give me things I want. Yeah, I don't know. There's probably a way to get the nice region in here. So I want that, and I want to go around the y-axis. So I'm looking at this. Here's my region. I'm going around the y-axis. Okay, so I need to draw a strip. And I've said this before, I'm going to say it every time. Your strip should always be perpendicular to your axis of rotation. So if you're going around the y-axis, you should have a horizontal strip. If you're going around the x-axis, you should have a vertical strip. That is always true. So when I rotate this strip around, right, I get a disk. And the volume of that disk is just pi times the radius squared times the thickness of the disk, which I'm going to call dy, right? A small change in y. So I need to find the radius as a function because the radius varies, right? Down here, the radius is just 1. Up here, the radius is large, but it varies. So I need to figure out, well, what is this function here? Again, this is y equals e, this is x equals 0, this is y equals 0, and this is y equal to the natural log of x. So the thing is, I can't just plug in y equals the natural log of x there because it doesn't make sense to do this, right? I'm not doing the integral of pi times the natural log of x squared dy. That's not right. This variable here has to match the variable I'm integrating with respect to. So instead of doing the natural log of x squared, I have to solve for x as a function of y. So if I've got y equal to the natural log of x, that's going to become x equal to e to the y, or e to the y equals e to the natural log of x, which is just x. Okay, so that's what's going to go in there. And then my limits of integration are as low as y equals 0, right? Because this can slide as low as 0 and as high as e. Now, we have to be careful here because you might look at that and think, oh, James, you've just given us the function we can't integrate. But that's not e to the y squared. It's e to the y quantity squared, which is e to the y times e to the y, which is e to the 2y. Bring the pi out. I mean, I didn't make a mistake necessarily, but I did set this up not the way I wanted to. I actually wanted this to be y equals 1. Right, y equals e is also fine, but it's not really, that's fine, it doesn't really matter. It's just going to be a weird answer. So I'm going to get pi times, what's the integral of e to the 2y? Well, I know the integral of e to the y is e to the y. The integral of e to the 2y is going to be e to the 2y. But I have to divide by 2 because the derivative would use the chain rule make us multiply by 2. So that division by 2 has to be counted. And this is one of those mini u substitutions where you don't actually have to do the u substitution. You say, oh yeah, the derivative would make me multiply by 2, so the antiderivative is going to make me divide by 2. From 0 to e. And then you're going to get something kind of funky. You're going to get pi times e to the 2e over 2. Again, if this had been 1, that would be a much more normal answer. Minus e to the 2 times 0 is just e to the 0, which is 1. 2. And that's how I would leave this answer. Times it. Okay, let's do another example. Kind of a classic example. I mean, not classic. Classic would be a bit strong there. So let's say we want to find the volume of the solid obtained by a revolving region bounded by y equal to the square root of 3x, yeah, right, and y equal to x about the x-axis. So you definitely want to draw these. If I was going to draw these, since I'm trying to find the region bounded by where these two what these enclose, I would set them equal to each other. Again, you could totally use Desmos, that would be fine. But setting these equal to each other and solving is not terrible. Square root of 3x equal to x, square both sides, 3x equals x squared, subtract, 0 is x squared minus 3x, factor out an x. So x equals 0, and x equals 3. Which makes sense, right? If x is 0, this is 0, and that's 0. If x is 3, this is 3, and the square of 3 times 3 is square root of just 3. So here's y equals x. And here's y equals the square root of 3x. So I'm looking for this region, and I'm going to revolve it around the x-axis. So I wonder if I can use my other rule for this. Oh man, sorry, I don't seem to. Oh, there we go. Maybe. I don't think you have an option of doing the function being two different functions. Oh well, that's too bad. That'd be nice. Yeah, I don't see that as an option. Oh well, such is life. So again, for this one, since our region is not flush with or against the axis of rotation, this calls for the Washroom method. And so I'm taking this little vertical strip perpendicular to the axis of rotation, always perpendicular, and rotating that around. Whoops. And when I rotate that around, if I just like draw it over here, it's going to draw this and mirror it down there. So I've got this. I've got, sorry, I just drawn this little part here. I've got that washer shape. And the volume of that washer, the volume of a washer is just the area of the big circle minus the area of the little circle. So pi times the big radius squared minus pi times the little radius squared, all times the thickness. The big radius is just the outer function, which is the one that's further away from the axis, which is the square root function. The inner radius is just the inner function, or the one that's closer to the axis of rotation. So in this particular problem, I know we're just about out of time here. I've got a minute left. Fine. So this particular problem, the volume of the washer is given by pi times The big radius is the square root function because that's a little further away from the axis. And then so that's the area of the bigger circle, and then we're subtracting the area of the circle that's removed. And then that's all times dx. So that's the volume of just this one washer here at some value x. And then we're going to add up all the washers from x equals 0 to x equals 3. And when I say add up, what I really mean is we're going to integrate from x equals 0 to x equals 3 of this minus this. I'm going to factor out the pi and have the square root of 3x squared minus x squared, which isn't too terrible. This ends up being pi times the integral from 0 to 3. Square root of 3x squared is just 3x. X squared is just x squared. And this ends up being, well, now I can just use the, right, I can integrate this and get pi times 3x squared over 2 minus x cubed over 3. And 0 to 3. Plug in the 3, and you get pi times 3 times 3 squared is 3 times 9, which is 27 over 2. 3 cubed is 27 over 3. And you could do this a number of ways. Oh, sorry, and I should mention that if you plug in 0, you're going to get 0. Right, 0 cubed, 0 squared, 0, 0 cubed, 0. You could say this is 9, and 27 over 2 is 13.5. So you get pi times 13.5 minus 9, which is pi times 4.5. Or if you prefer, 9 pi over 2. There's other ways you could tackle this. You could factor out a 27 and say you've got 27 times 1/2 minus 1/3. And then that's 27 times 3, 6 minus 2, 6, which is 27 times 1, 6. Which reduces to 9 over 2. Either way is fine, whatever you want to do. So there's a couple examples about finding volume. All right, that's all the time we have for today, but please do send me whatever emails or other messages you want to send, and I will try to give you some specific examples of the various things you guys are asking about. Go fill out the attendance and take care. I'll see you guys on Tuesday, but I'll make some videos in the meantime.